Okay, Sebastian is going to continue with his second talk on constant mean curvature surface and integrability. Go ahead.
So, yeah, thanks, and sorry again for the delay due to some technical problems. And yeah, yesterday we started to discuss some gauge theoretic description of minimal surfaces in S3 and their relationship to constant mean curvature surfaces in R3. And I will continue with that today. So let me just remind the setup. We have a conformal immersion from a Riemann surface into S3, which we think of as the compact Lie group SU2. And what we did was we looked at the equation, the integrability condition, or the Maurer-Catani equation. D nabla df is 0. This is the Maurer-Catani equation, where nabla is somehow the pullback via f of the Levi-Civita connection, which itself is the mean of the left trivialized connection on the Lie group SU2 plus the trivial connection given by the right trivialization. So yeah, in formulas, this just means if you use left trivialization, then the connection, the Levi-Civita connection, is just given by 1/2 G inverse dg, where this one form, the Maurer-Catani form, acts by a joint representation. And then, if we now look at conformal and harmonic maps, then, so meaning minimal surfaces, this means that we also have the harmonicity equation, namely d nabla star df is 0. So we have this coupled system of PDEs, and of course this will be, or this is an elliptic nonlinear PDE. And yeah, what we do now is something similar to what we did yesterday with maps into R3. We use the identification of the Lie algebra with the skew Hermitian 2x2 matrices and its complexification, which are the trace-free SL2C matrices the trace-free 2x2 matrices, and we use this to decompose into complex linear and complex antilinear part. So to start with, I take the pullback of a Maurer-Catani form or the differential, and I denote it by phi. So this somehow corresponds to 1/2 df. I decompose it into complex linear part. So this is a 1,0 form with values in the trace-free anamorphisms, and this is a 0,1 form. And because, yeah, again, as yesterday, because we have skew, because this form is a 1 form on sigma with values in the skew Hermitian trace-free anamorphisms, the 0,1 part is minus the adjoint of the 1,0 part. So we really have this decomposition as written down. And now we can do the following reformulation of this set of equations. And so yeah, what we get is the following. So first we have that the connection nabla, which was the pullback connection, plus phi minus phi star. So this is the connection D plus F inverse dF. So it's the gauge by the immersion F of the trivial connection. So this connection is actually a trivial connection. So it's globally flat, and we have global flat parallel sections. And likewise, nabla minus phi plus phi star, in our notation, this is D plus 1/2 F inverse dF minus 1/2 F inverse dF. So it's just D. So it's also a trivial connection, meaning that we have a global frame of parallel sections of this bundle with respect to this connection. So from that we get a curvature condition, namely the curvature of our connection here, plus again with no, we have a minus sign here, of course, minus 1/2 phi wedge phi star is 0. So this is somehow, can be seen again as the Gauss equation for our surfaces. And the two equations, our Cartan equation and the harmonicity equation give us, because we can rewrite phi is somehow 1/2 times 1/2 F inverse dF, and then minus I star F inverse dF. So this is the complex linear part. Okay, I have here 1/2 again. So this is just basically by direct computation. If I compute the linear part of a one form, or the 1-0 part of a one form, I use this formula. And if I know that d nabla F inverse dF is 0 and d nabla of star F inverse dF is 0, this just means that I get d nabla phi is 0 from my equation. But it turns out, because phi is a 1-0 form, I just take somehow the holomorphic part, so the 0-1 part of the derivative. So if you look at I will go more into detail in this direction today, but let me just shortly explain what it somehow means. So if you have an ordinary one form on a Riemann surface, and it looks like it's a 1-0 form, so it's given by a smooth function f times dz. So then the exterior derivative, just the trivial connection applied as an exterior derivative to this form dz, gives us df wedge dz. But this is the same as somehow the 0-1 part of the derivative of f. So we just take the derivative with respect to del by del z bar, wedge dz. And here we do the same. We just look at the complex antilinear part of the derivative, or the holomorphic derivative. And of course, because phi star is the adjoint and the connection nabla is unitary, this just means that del nabla phi star is 0. So we get, again, similar equations than yesterday. So we get that nabla plus lambda inverse phi minus lambda phi star. This is trivial for lambda is 1 and minus 1. But now, due to the fact that that d nabla of this phi and d nabla of this phi star is also 0, I can do the following observation and flat. This is the important observation here for all lambda in S1. And I write plus unitary. So let me first prove that. So I compute the curvature of this connection, lambda inverse phi minus lambda phi star. And if I do this computation, I get, of course, the curvature of nabla plus then 1/2 phi wedge minus phi star. So I get a minus here, phi star. And then I get plus d or lambda inverse d nabla phi plus or minus lambda d nabla phi star. But the last two terms are vanishing by our observation that our connection is our harmonic map is our immersion f is harmonic. So we observe that these two terms vanish, and so this is just the curvature of the connection at lambda is 1 or minus 1, and this is 0 because the connection is trivial. So this is a crucial observation here. These connections, nabla lambda, they are flat. So nabla lambda is flat for all lambda in S1, but actually it turns out for all lambda in C star, somehow the complex numbers without zero. So this holds in general for harmonic maps into compact Lie groups with their B-invariant metric, but in particular it holds for minimal surfaces. And the extra condition that we have a minimal surface means that the map F is conformal, and F is minimal, implies that F is conformal, and this implies that if we take or if we compute the derivative of the immersion, which is given by this phi minus phi star, basically, we can compute out of phi and phi star the induced metric. This is just given by some trace, and then a short linear algebra computation gives us that this means, or is equivalent actually, to the fact that the determinant of phi of the 1-0 part of the derivative is
Sebastian,
0. Yes.
I think the screen is frozen.
Oh yes, I just see that. Let me see why this happens.
Push it forward.
Delay. It should still be connected. So
I think if it's the browser, you should push it forward. Maybe that's the point.
Okay.
Or is it?
It's a little bit strange.
I think okay, second and third.
Okay, now I see. Oh.
Okay, second one
sorry.
is here.
I have to. I have to push to the next slide every.
I see. So you're projecting from desktop and
Yes.
writing from iPad. I see.
Yeah, I'm sorry for the delay. So I hope you got a little bit of the idea. So let me remind what I have just said. And okay. So the important thing, let me just start a new page, is that so important observation. If we decompose the derivative of the differential of the Maurer-Cartan form, or the pullback of the Maurer-Cartan form, into its 1-0 part and its 0-1 part, which is minus the adjoint of the 1-0 part, then we can add to the pullback of the Levi-Civita connection the lambda inverse, the 1-0 part, and we can scale this again, and we can subtract different scaling of the 0-1 part, and this is a flat connection for all lambda in C star. And additionally, we are just from the observation that lambda inverse is lambda bar if lambda is in the unit circle, which sorry, I again forgot to switch. You have to remember me directly if I write something. So from the observation that if lambda inverse, if lambda is in the unit circle, then lambda inverse is the same as lambda bar. This gives us the fact that these connections which I denote by nabla lambda, are actually unitary. So therefore, nabla lambda is a Hermitian or unitary connection for all lambda in S1. So and the final observation is that for lambda is 1 and minus 1, nabla lambda is trivial. So we have globally parallel frames, and somehow computing the gauge between these flat frames gives us back the immersion. So we get nabla 1 is the gauge transformation of nabla at lambda is minus 1 by the immersion F. There F is the minimal surface. So this is some kind of reconstruction formula of minimal surfaces, or more generally harmonic maps into SU2, or more generally into compact Lie groups in terms of families of flat connections. So this is true basically always. If we have such kind of family of that form, which is flat for all lambda, which has the property that these are unitary, and finally that they are trivial, then we automatically get a harmonic map. And additionally, if the 1,0 part, so if that the determinant of the 1,0 part is 0, then the map F is conformal and hence a minimal surface, maybe with some branch points. So we aim to construct minimal surfaces in S3, or similarly by integrating up the differential or the rotated differential into R3, is to construct such kinds of families of flat connections with these properties. So aim construction of families or of
next page.
Oh yeah, next page. So thanks again. So the aim is to construct families of flat connections with these properties of suitable families of flat connections. And so basically this was known before I entered that business, and it has been carried out in some special situations quite successfully. So let me just give some historical remarks. So in case of a sphere, of a Riemann surface, a compact Riemann surface of genus 0, we already know that that they're the only minimal or CMC spheres due to the vanishing of the Hopf differential must be totally umbilic, so it must be round spheres. But again, we can see this in this setup, because on a sphere, which is of course simply connected, there are not many different flat connections. And so remark for spheres, all nabla lambda are trivial, and this tells us, or we can reinterpret this, that only round spheres are possible. So this is somehow a very boring case, of course. But then the next more interesting case is that of genus 1 surfaces. So of CMC tori or minimal tori in the free sphere. And of course, at least the embedded ones have been classified recently by by work of first Simon Brandle, who solved the Lawson conjecture that the only minimal embedded tori, genus 1 surface in the free sphere is the Clifford torus. And later on, Andrews and Lee built up on that technique of Brandle and proved that this basically classified the embedded constant mean curvature surfaces in the free sphere. But one can describe all these surfaces in terms of somehow algebraic geometric data using this associated family of flat connection. So the thing is, there is a so-called spectral curve X, which is a Riemann surface, or more concrete or more specific. It's a algebraic curve. It has possible singularities, but usually they do not occur. And it has some additional data, namely meromorphic differentials. And some holomorphic line bundle. And these data, the spectral curve, somehow which parameterizes via these differentials and the line bundle, these families of flat connections. So the important observation, which is due to Hitchin, Pinkel, Sterling, and then also Bobenko, is that CMC tori can really be described in terms of algebraic geometric data. There's this algebraic curve X, there are these specific meromorphic differentials satisfying some additional properties, like certain integrals need to be integer valued, and a line bundle which needs to satisfy a reality condition. And then in terms of these data, it's possible to write down the families of flat connection. But unfortunately, or somehow, not so surprisingly, this approach doesn't generalize to higher genus surfaces. And the reason for that is, in the case, this time I think of it, in the case of a torus, the fundamental group is still abelian. So all the monodromies, or the monodromy matrices of connections are commuting. So what you usually get is two parallel eigenline bundles which span the whole rank 2 vector bundle, and then the connection can be somehow specified by determine this line bundle and determine the monodromy of this line bundle connection, and everything reduces to an abelian theory. So things really simplify in case of the abelian monodromy. But one can show, and basically this was one of my first works into this direction, that if F is a minimal surface, a compact minimal surface of genus bigger or equal than 2, then these connections nabla lambda are irreducible for generic lambda in C star. And irreducible means we do not get any parallel subbundles. So the monodromy representation, if we start at one point of the surface and we go along a closed loop, a topologically non-trivial closed loop, we can produce the flat or the parallel frame along this loop, and we get some monodromy. And if we choose a different loop and all the possible loops along the different elements in the first fundamental group, we obtain monodromy matrices which are not commuting. And this makes the approach of Hitchin and Pinkel-Sterling and Bobenko not work in the case of genus greater or equal than 2. So we have to come up with a different theory or try to develop different techniques. And so the aim today is to introduce you to some basic over Riemann surfaces and holomorphic bundles over Riemann surfaces. So yeah, we will use that knowledge to really describe these minimal surfaces in the free sphere, and likewise CMC surfaces in the free sphere. So yeah, let me start with the topic of the second talk, namely holomorphic bundles and flat connections over compact Riemann surfaces. And I shall first say something about these holomorphic bundles. So we have a complex vector bundle over our Riemann surface, and the bundle is a holomorphic bundle. So a complex vector bundle V is holomorphic if we choose a co-cycle of co-cycle maps such that the transition functions, if there is a choice or of a trivialization of this complex vector bundle such that the co-cycle maps G alpha beta induced by the different trivializations on the intersections of open subsets of our Riemann surface into, now it depends on what kind of bundles we look at. Usually we take the SL2C bundles, but of course we can use more general GLNC bundles. But we impose the condition that these co-cycle maps are holomorphic. So that's the standard definition of a holomorphic vector bundle over Riemann surface, or more generally, it clearly holds for complex manifolds as well. And the basic examples we already discussed yesterday was that of a canonical bundle of the Riemann surface. So we have locally, we have maybe two different Z and W holomorphic charts, and then dz and dw give us local trivializations of the canonical bundle over sigma. And the standard computation is that dz is just dz over dw, the derivative of z with respect to w, times dw. And clearly this is a holomorphic. I suppose you can still read the last arrow, right? Yeah, it should work. So this this is just the holomorphic co-cycle map with respect to these different local trivializations. So the canonical bundle is just a particular example of a holomorphic vector bundle. Okay, so if we have a holomorphic vector bundle over a Riemann surface, and if we have a subset U subset 0, which should be open, then we get the space of holomorphic sections in this holomorphic bundle. So this is the space of holomorphic sections, and a section is clearly holomorphic if in these trivializations for which the co-cycle maps are holomorphic, if for these we get that in all the trivializations, the section is a holomorphic map into the trivial bundle C to the n. So if it's just given locally in the trivialization by holomorphic functions. And then, of course, as an example, if sigma is compact, then H0, the space of holomorphic section of the whole on the whole Riemann surface, is finite dimensional. And in particular, we get the dimension of the space of holomorphic section of the canonical bundle is exactly G, the complex dimension. Okay, and we will often use the relationship between holomorphic bundles and flat connection. And this comes from the observation that holomorphic bundles can be described likewise by specific differential operators. And this works as follows. So we call, oh, something happened.
Next page, okay.
Yes, sorry again. So we want to describe holomorphic bundles via so-called holomorphic structures. These are differential operators from the space of sections in a complex vector bundle into the 0-1 forms on sigma, so into the space of sections in the bundle K bar tensor, of course, over the complex numbers tensor V, such that we have the Leibniz rule, but only for the 0-1 part. So such that del bar, we take a section and multiply it with some function f, then this should be the same as we take the differential of f and look at the 0-1 part, the complex antilinear part of the differential, which vanishes if f is holomorphic, of course, tensor s plus tensor with section s plus the function f times the holomorphic structure applied to s. So we look for these kinds of operators, and it turns out that every holomorphic bundle automatically has such kind of holomorphic structure, this kind of elliptic differential operator. And the proof is quite simple. If we have local holomorphic trivializations of a bundle, so we have these sections S1 times and so on times SR, where R is the rank of the complex vector bundle, then we can write every section, at least locally, as a linear combination of these holomorphic sections and times SI. And we define del bar of the section S to be just the sum over I, and then we take the 0-1 part of the derivatives of these pre-functions fi, and we tensor it with si. And because the cocycle is holomorphic, it turns out that this is well defined. So this is just a standard computation in differential geometry, I guess, to compute what comes out if you use a different frame, which is related by the holomorphic cocycle map, and then it's just directly comes out that you get the same result. So this is globally well defined. So we have a holomorphic structure, and it satisfies the following very important property: the space of holomorphic sections in V over some subset is exactly the kernel of the operator del bar if we restrict to sections which are only defined on U. So, the kernel gives us the holomorphic sections. And particularly this shows that, or this gives one way of showing that the space of holomorphic sections on the compact Riemann surface is always finite dimensional, because it's the kernel of an elliptic operator. These del bar operators are really elliptic operators. They square basically to the Laplacian. And this means that we get finite dimensional spaces. And then, there's the converse of that, namely, we do get the following. So let del bar be a holomorphic structure on the complex vector bundle V to V over sigma. Then V is a holomorphic vector bundle, as follows. So one can prove, there are different proofs. So I think there are proofs which just use linear PDE theory or standard linear elliptic theory of differential operators. But also there's a nice proof in the famous Atiyah-Bott paper, there they show that if you have a holomorphic structure on a complex vector bundle over a Riemann surface, you automatically get locally holomorphic sections which span the vector bundle. So locally, so if we restrict to small open neighborhoods of arbitrary points, there exists frames given by sections S1 to SR. R is the rank of a bundle with a property such that the del bar of Si is 0 for all I is 1 to R. And this works always locally. So if we now compute the transition functions between such kind of frames, which are holomorphic in the sense that the del bar of it is 0, then automatically the transition functions or the co-cycle maps of these frames are holomorphic. Just by the Leibniz rule, or the 0-1 part of the Leibniz rule of these holomorphic structures, of these del bar operators. And this means whenever we get such kind of an operator, our holomorphic, our complex vector bundle is a holomorphic vector bundle. And we will make use of that because of the following because of the following observation, that we get quite simply from flat connections, or more generally from connections, we get such kind of operators, namely a connection or a flat connection. Or maybe I should first say any connection.
Next page.
Next page, thanks for reminding me. A connection nabla, a complex connection nabla, on a complex vector bundle V over the Riemann surface induces a holomorphic structure del bar nabla, a holomorphic structure del bar nabla, and this works quite easily. So we think of nabla as an operator which maps sections to one forms, and we decompose these one forms into the complex linear part, the 1-0 part, plus the 0, 1 part. And then the Leibniz rule for connections automatically gives us that the del bar part, or the 0, 1 part, satisfies the Leibniz rule we impose for holomorphic structures. So we automatically get a holomorphic vector bundle from a connection. And we have the following crucial observation: a complex connection maybe first some notation. Or definition. If V is a holomorphic vector bundle with holomorphic structure del bar, a connection nabla is called compatible with del bar if, or with the holomorphic vector bundle structure, if and only if we have that this induced holomorphic structure from the connection is just the given one from the holomorphic vector bundle structure. So if we have this property, and then the lemma we will use is the following: the connection nabla is flat if and only if it is holomorphic, meaning that the connection 1 forms for local holomorphic frames are holomorphic. So in a very specific sense, it means that, that if we describe the connection in terms of connection 1 forms, then if we take a holomorphic, if we take a holomorphic section, then the connection 1 form is again holomorphic. And I think I should prove this, or at least indicate how this works. So if we have this holomorphic frame, S1 up to SR, then we know that, or by definition of a compatibility of the holomorphic bundle with the holomorphic structure induced by the connection, it means that nabla Si is just del nabla Si. It's just the 1, 0 part, and the del bar nabla Si is vanishing. So if we write this as a sum over J omega Ji times Sj, it means that the omega Ji are 1, 0 forms. And on a Riemann surface, a 1, 0 form, wedge of 1, 0 form is automatically 0. So this means that the curvature, it's usually given by somehow sum over this d applied to the section Si d omega Ji, and then I need a wedge, but the wedge part, because both forms are 1, 0, this wedge part automatically vanishes. So we just get the exterior derivatives of these 1, 0 forms, and this vanishes if and only if all the connection 1 forms omega Ij are closed and this is equivalent to the fact that they are holomorphic. So in a specific sense, yeah, flat connection on Riemann surfaces are basically the same thing as some holomorphic objects. And we will use that later on to really construct certain holomorphic maps which describe minimal surfaces. So we will need some additional properties. And the next one, okay, I think I have to prepare the blackboard. Just a second, please. Okay. So now I'm on page 12. That's fine. So what we need is not only flat connections, but also we need unitary flat connections. And there's a long going story which started with I think Chern. So if we have a Hermitian metric on a complex vector bundle V over our Riemann surface, but of course this works more generally over complex manifolds, then there's a unique connection which is Nabla or Nabla-Chern, the Chern connection, which is compatible with the holomorphic structure del bar and with respect to the Hermitian metric, and we call this property unitarity, unitary. So the last property just means that if we take the derivative of two sections, if we take the derivative of the Hermitian metric applied to two sections, we get that this is the same as Nabla S T plus S Nabla T. And then the observation of Chern was that if we specify the 0,1 part, it also automatically specifies the 1,0 part. And this can be done, for example, by defining Nabla to be del plus del bar. The del bar comes from the holomorphic vector bundle structure, and the del is defined to be the adjoint operator to del bar. So to be more specific, what we do is we have a section T in this bundle V. We map it to the bundle, to the dual bundle by using the Hermitian metric. So this is of course complex antilinear. When we take the induced del bar operator, it gives us a section in K bar, the dual. So this is by somehow taking the del bar of this section, and then we again apply the Hermitian metric to a one form with values in the bundle, and this is a complex antilinear map. Again, it maps to K sections in KV by applying the Hermitian metric again, and overall we get a well-defined map which we can call del bar star, and it's really the missing part, which the 1,0 part of a connection. So this sum, if we define this operator del as by this composition, then we really get a connection, and this is the Chern connection. And a natural question, at least in our situation, is whether a holomorphic bundle admits a unitary flat connection. And we need that because of the following. So let me just remind you, we have constructed families of flat connections, nabla lambda, which are flat and unitary for all lambda in S1. So if we look at the 0,1 parts, we have holomorphic vector bundles. And then there's the question, is there a connection which can be unitary? And we get to an important notation. So, to the notation of stability of a holomorphic vector bundle, V over Riemann surface sigma. So the question we want to answer is whether this vector bundle can have a holomorphic unitary flat connection which induces something holomorphic, and the answer is that we need a condition, namely the condition that it's stable. So in the rank definition only for SL2C bundles, so rank 2 bundles V to sigma of rank 2 with the property that the determinant bundle, or likewise the degree of V is 0. And then we say such bundle is stable, is called stable, or likewise semi-stable, if all holomorphic subbundles, line subbundles, so subbundles of rank 1, are of negative, in the case of stable, or non-positive degree. So this is a notion which comes from algebraic geometry, but it turns out that it's very much related to unitary connections. Namely, there's this famous theorem of Narasimhan-Seshadri from the 1960s, I guess. So it says a holomorphic bundle is stable if and only if it admits a compatible unitary flat connection. And if it's semi-stable, then sometimes it also admits a unitary flat connection, but this is corresponding to the reducible flat connection. So these are special and we do not encounter them so often. So I will focus today on these stable bundles. And I should give a proof of this. And let me shift pages. So yeah, let me try to indicate the proof. So it's by computation. So we cannot give a full proof because the reverse direction that if we have a stable holomorphic bundle, there's a unitary connection, which this is quite complicated and not easy. But the reverse condition that stability is necessary is simple. It's a nice differential geometric or complex geometric computation. Namely, what we do is the following: we write down this holomorphic subbundle So we just assume we have a holomorphic line subbundle L. And now we have a Hermitian metric, which is unitary. So we just prove this direction. So we can decompose as a complex vector bundle into L plus the orthogonal complement, L plus L perp. And then we can decompose the flat connection as a line bundle connection on L. And it's the orthogonal complement. And then the off-diagonal terms, alpha and beta. We have done similar things yesterday. And by assumption that L is a holomorphic line subbundle, so it's given in terms of holomorphic inclusion maps, it turns out that this alpha needs to be a 1-0 form. It's a section in sigma k, and then it maps sections in L to the minus 1, so it's a section in k times L to the minus 2. So it's a 1-0 form as L is holomorphic. So that's here the important observation. And then unitarity means beta is just minus alpha, the adjoint of alpha, with respect to the Hermitian metric. And this, of course, is a section in k bar L squared. And we have that the curvature is flat. The curvature is vanishing of nabla. So we compute the curvature of the first component, and this gives us 0 must be the curvature of the bundle L plus alpha wedge alpha star. So if we integrate up, we get that the degree of the line bundle L, the topological degree, is given by a rescaling of the integral over the curvature by Chern-Weil theory. So we take that curvature and integrate it up. And due to this observation here, we can easily see that this is less or equal than 0 with equality if alpha is 0, if and only if alpha is 0. So we get automatically that if we have a holomorphic, if we have a flat unitary connection which induces the holomorphic structure is semi-stable because every holomorphic line subbundle has negative or non-positive degree. And if the connection is actually irreducible, which means in particular that alpha must be different to 0, then we also get automatically stability. So there is a strong relationship between notions from algebraic geometry, from holomorphic objects on compact Riemann surfaces, and these irreducible flat unitary connections we are interested in. Okay, so right, maybe we need another important observation. So we not only have unitary connections, but away from the unit circle, from lambda in the unit circle, we just have flat connections which are not unitary anymore. And now we look at the following. So if nabla is a flat connection, and if we add a 1-0 form, phi, a section in K, and then in the maybe trace-free anamorphisms of the bundle V, then nabla plus phi is flat if and only if phi is holomorphic. So basically, this is the same computation as in the lemma before. So if we if we do the computation, f nabla plus phi, this is the curvature of nabla plus the exterior derivative of phi, but and then 1/2 phi wedge phi, but phi is a 1-0 form. It's a section K, so complex linear one form, and this means this summand vanishes, and what remains is the curvature of the original connection plus, and again, because phi is a 1-0 form, we just need to look at the 0-1 part of the derivative, and yeah, the statement follows. So if we add to a flat connection a 1-0 form, then this is again a flat connection if and only if the 1-0 form is holomorphic. So we get a strong relationship between these flat connections and holomorphic vector bundles. And it also shows if we specify a holomorphic structure on a vector bundle, there is at most a finite dimensional space of flat connections, because every two flat connections differ by a holomorphic one form, and we just discussed before that the space of holomorphic sections of a vector bundle, like one forms with values in a morphism bundle, is a finite dimensional space. So we have these finite dimensional affine spaces in which we can look for flat connections. Okay, are there any questions so far? So these are the objects we have to encounter, and then in order to really construct surfaces, it was observed over the last decades that one has to go one step further. Namely, if we have compact surfaces, we do not really know the knowledge about all the what exactly are the flat connections, but we have some kind of freedom. And this was first observed in the case of tori, where we get, due to the work of Hitchin, these spectral data, the algebraic curve X and some meromorphic differentials. And it turns out that these data are equivalent to the fact that we only describe the gauge classes of the connections. So by gauge classes, let me just make this more explicit, because it's quite important in the following. So if we have just some connection, nabla, on a complex vector bundle, and we have a map G from, let's now stick to a special case on the bundle V, which is just the trivial C2 bundle over our Riemann surface. And then the space of gauge transformation is the space of maps G into the group SL2C. And then G acts as a gauge transformation, namely we can, from the right, we can look at the operator which is given by, I take a section, I map it via G to a new section, I apply the operator nabla, and then I map it back via the inverse map G inverse to a section. And it turns out that this is a new connection, and it's called the gauged, or the gauge of nabla by G, and denoted by nabla point G. So in the case of a trivial bundle, we look at connections which are given by connection one forms. So D plus nabla is D plus omega, and we stick to SL2C connections. So omega is a one form on sigma with values in the trace-free endomorphisms. And then one can compute that the gauge connection is D plus G inverse DG, and then we have G inverse omega G. So we let G act by a joint representation on the connection 1 form, but also we have to take this derivative into account. And particularly, it's clear that if we start with a flat connection nabla, so this works generally for all complex connections. If we start with a flat connection nabla, and if we apply the gauge transformation G, then we get a new flat connection. So either we compute the curvature of the gauge connection and see that it's flat, or we observe that flatness is equivalent to the fact that locally we have parallel sections, which many parallel sections. So we have parallel frames of the bundle. And then if we have a parallel frame of the flat connection nabla, also the connection nabla gauged by G has a parallel frame, namely the frame G inverse of the original parallel frame with respect to nabla. So if nabla is flat, also nabla point G is flat. This automatically holds. And then I think it started with physicists, but it's also quite important in mathematics, the whole field of gauge theory. So if we look at the space of all connections, it's an infinite dimensional space. It's an affine space over this space of sections of the one forms with values in the corresponding endomorphism bundle. And we have the infinite dimensional space of flat connections. So let me denote AF, the space of flat connections on, or flat SL to C connections. So the connection 1 forms are given by trace-free 1 forms on our trivial bundle V. And we have the gauge group, so the group of gauge transformations, and the group structure is just given by pointwise multiplication into SL to C. And I do not go into the analytic problems here. Of course, one has to think about which topology on this infinite dimensional space is appropriate, what kind of regularity for the maps we consider. There are different possible approaches, but let's just think we just look at smooth maps here. And then what we let's denote this by the complex gauge group. Then we get the space, the quotient space. Namely, what we do is, we denote it by the Riemann moduli space. It's just the space of flat connections modulo this infinite dimensional space of gauge transformations. And it turns out that this is it's a finite dimensional space. It's a complex analytic variety, but yet in general it has non-smooth points. If we restrict to irreducible flat connections, so irreducible means we do not have any parallel sub-bundles globally. There are no global parallel frames or something like that. So if we have this additional condition on the flat connections, then we get that this space is a smooth complex manifold, or just a complex manifold of dimension 3 genus of of complex dimension 6 the genus of our Riemann surface, of our compact Riemann surface, sigma minus 6 in the case of SL to C bundles. It's a finite dimensional space. And then if we put we put the reducible or the totally reducible points, we get still a nice complex analytic space. So M, the Riemann moduli space, is the space of flat connections by this gauge group, and it's still a somehow nice complex analytic space of the same dimension, but of course with some kind of singularities. And we will, I think I do not have too much time left, but we will see tomorrow basically that we only need to consider holomorphic maps into this space here, into this finite dimensional space. So in order to construct harmonic maps into compact Lie groups, or to construct minimal surfaces in the free sphere, or CMC surfaces in R3. So instead of solving nonlinear PDEs to solve the Gauss-Codazzi equation or apply some kind of minimization process like the plateau solution, we can describe these maps, these harmonic maps or minimal surfaces, in terms of complex curves into these finite dimensional manifolds. So this is an important observation. So maybe it's I will not be able to tell you everything I wanted to tell you today, but let me just mention some important observation about this complex manifold here. Namely, we can identify it via the monodromy. So we get that the monodromy representations of flat connections. So we have some kind of Riemann surface, let's say of genus 2. We have our basis of the first fundamental group, or the generators, and so we have alpha 1, beta 1, alpha 2, beta 2, and so on. And as I said before, if you have a flat connection, we can compute the parallel frame along these curves, and it doesn't. The parallel frame, or the monodromy of the parallel frame, mainly to what it comes back if we move a closed curve. This doesn't depend on the choice of a path in a given homotopy class. So so we get a map from the first fundamental group of our Riemann surface based at a point P into the space of endomorphisms or invertible endomorphisms of the fiber of so into GL of the fiber. But in our case, we know that we have SL2C connections, so actually we map into SL2C in our situation. And this is the monodromy representation. And it's basically clear that this monodromy representation, it's specified because if we have a parallel frame along one curve and we go along another curve, we just do the composition of the product of the two monodromy matrices specified by A1 up to BG, which are SL2C matrices. So we have we have 2G many SL2C matrices, but then if we apply a gauge transformation, it changes these monodromy representation by conjugation. By conjugation with the gauge transformation at the prescribed fiber over the point P. And so what we get is basically this monodromy. So maybe the last theorem for today. So the RAM moduli space is complex biholomorphic to the so-called Betti moduli space, and this is via monodromy. And the Betti moduli space is the space of matrices A1 up to BG, which satisfy the natural relationship of the monodromies on a compact Riemann surface of genus G, or it's the space of representations from the first fundamental group of sigma into SL to C modulo overall conjugation by SL to C matrices. And if you do the computation, you at least see that the dimension of this Betti moduli space, at least at the smooth points, is again 3G minus 3. 6G minus 6. So an SL to C matrix is the space SL to C is three-dimensional. You have but you have 2G many of these SL to C matrices, but then you have this overall conjugation which subtracts you 3 dimensions, and then you have this implicit equation on these matrices, which at least at the irreducible one is a submersive equation, and then you see that the Betti moduli space is really at its smooth point a 6G minus 6-dimensional complex manifold. So, but the important thing is that it's really equivalent or as a complex manifold to the Betti moduli space. So what we will do tomorrow is to see how we can describe curves, or so curves into these moduli spaces. So we have the family of flat connections, and for lambda in C star, and this gives a map. Lambda in C star maps to the gauge class. Nabla lambda is its gauge class, or the corresponding monodromy representation up to conjugation. And we will study these curves and try to see how many informations we get out of that. And then in the last talk, I will explain how, at least in some particular examples, we really can construct explicitly curves which satisfy all the conditions we need to reconstruct harmonic maps or minimal surfaces, and to obtain certain interesting and nice and maybe surprising informations about these minimal surfaces. So I think I should stop now, and maybe you have some questions.
Any questions? All right, thank you very much. So we are waiting for the applications patiently. Thank you very much.
You're welcome.